I hope I'm somewhat provocative with the title. Built my first predictive model back in '95. It was an artificial neural network, so I've been at this for a while. And the longer I do that, the more interesting cases that I run into are whenever models are performing too well. And not because I messed up with holdout sets and like not for kind of bad technical reasons, but fundamentally there is something wrong when models perform too well. And I want to show you a couple of examples that hopefully kind of share some of the insights around that, why predictability may in fact be a predicament. So what do I even mean by predictability? So if you think about building models that can predict things or classify things, all of that technology that is now kind of bundled in AI, but I might mostly speak here about supervised machine learning, there's really kind of a continuous scale of how well you can predict in the best of all cases. And so some things we know that we can't predict, or that we shouldn't really be good at predicting. And so an example of that is the stock market. I mean, if you get an accuracy of 60%, you're not sitting here. You're owning an island somewhere in the Bahamas, right? So we know that the stock market is one of those things you should not be able to predict. Fundamentally impossible to get really high accuracies. On the other hand, you have a lot of recent development in deep learning on a problem of this sort. Is this a cat? Now, I'm not saying it's easy to build a model to do that. That took us decades to get there. But any 3-year-old is a lot better at this than your financial advisor at that. So that's what I mean by there is this scale of how well you can do in the best of all scenarios. Now, my day-to-day life and the things that I find most interesting in terms of applying machine learning is neither of those two cases, but I'm interested in predicting human behavior. And what's fascinating about human behavior is you see the same scale again. Because on one side you have things like sexual orientation. There was a very famous article published from a group working on Facebook. Basically they sell, like with a little bit of information about your likes, they can predict anything from your religion to gender to sexual orientation, all of it. On the other hand, I have no idea what I will have for dinner tonight. Sorry. I mean, whatever they offer in the trains over to Frankfurt, I have no clue. So there are things about my life I can't predict at all. And so you have again this kind of range of how easy it is to predict certain things. So why does it matter? Let me show you what happens technically when you look at this range. So let's start by predicting who is male. And we'll do that on that Facebook data set that has been published, where you have basically these anonymized IDs, and alongside with it you have a gender column. And you also have self-reported kind of day of birth and so on. In addition to this, you also have a data set kind of all of the likes, and it's anonymized as well. So it doesn't really matter how we do this. For the sake of argument, I'll use logistic regression, my kind of favorite. So the story of my career has been, I started out with artificial neural networks in '95. I did my PhD downgrading to decision trees in 2003, and these days I do everything I do with logistic regression, so feel free to talk to me about that. Okay, first experiment we'll do. How well do you think I can predict gender purely based on age? That's kind of on the stock market side of things, right? I mean, okay. There's very little signal, and not surprisingly, the accuracy is 60%. Well, given that the base rate was 40% male, again, no surprise here whatsoever. But that's not really very interesting. What I care more about is how well I'm actually kind of discriminating. So the ranking, the accuracy here, the AUC is 58%, and if 50% is random and 100% is deterministic, yes, we are definitely on the stock market side of things. But what I really want to show you is this. This is the distribution of the predictions. So, okay, fine, I have test set, hold out, I make predictions there. This is a histogram of the predicted probabilities from my logistic regression. Most of the applications today, you don't care about accuracy and you don't care about AUC. What we want to do with these things, at least in marketing and probably many others, is you want to recommend something to the top largest predictions. So for instance, if I need to target males, then guess what I'm trying to do? I'm going to only look at those predictions that were the highest. So I'm usually interested in the extreme predictions for many, many applications, recommender systems, and so on. Now guess what happens out here? While the model overall is pretty awful, I'm actually not that bad. I get 75% male in the top 1% predictions. Decent. Now, let's move on to, and we promised in the introductions to not have the debates about big and bigger data, but I'm going to throw in all of the likes. So, how well do you think I can predict gender based on your likes? Accuracy is 83%. It's actually a little bit disappointing. I was hoping for better, but this is interesting. This is a very opinionated model. This model knows that it knows something. So you see how what originally was kind of this almost normal distribution in the middle, all of a sudden it's really kind of bimodal. It's either 0 or 1. And to no surprise, out here, you get 100% correct. By the way, what's going on there? What's happening to those people where the model seems to be unable to make up its mind what the gender is given the likes? Who are those people where the model is clueless? So, depending the audience you ask, if you ask a marketing audience, they will tell you something about these kind of new transgender movements and I don't know what. If you ask a more technical computer science audience, they will tell you that they're probably sharing accounts with their significant other. And if you ask a data science group, so nobody raised their voice, they will tell you, well, obviously, these are the people without any likes. It's a data problem. These are the people without any likes. So we're back to H, and guess what? That's when the model has no opinion. Okay, so why did I show you all this? I think it's really interesting to think about this progression when initially this is what the distribution of prediction looks like. And now I'm going to add more and more likes, not based on predictability, just because they're most common. So with the 10 most common likes, this is the next cut, and you see how this kind of opinionatedness of the model shines through. The distribution of the prediction gets more and more extreme, and already with 100 likes, I get 100% correct in the top 1% of predictions. And so it goes until you end up with the final results I showed you. So the takeaway here is, when things get very predictable, the predictions get very extreme, which is kind of obvious, but not necessarily something that you think about on a daily basis. Now, again, why do I tell you all this? Well, most problems I meet are kind of mixtures of both. It's typically not one or the other, but there is a part of the problem that has this very strong part of randomness, and there is a second part to it where you find a lot of determinism. So the task typically is not uniform in how predictable it is. And I'll show you a couple of examples where this plays mostly against you, but on occasion it actually helps. So, and at this point I have to come clear what I do for a living. I work in what's called programmatic advertising. So I'm working for one of these companies that you probably curse every time you see ads all over your computer. So for instance, when the New York Times loads, the majority of these ads were sold in real time in an auction. So these auctions, we're talking about order of 100 billion auctions are executed every day. And we are one of the companies that are bidding in these auctions on behalf of clients, like cars, brands, to show ads. So what my day job is, I need to build models to predict all kinds of digital events that my clients, which are brands and advertisers, are interested in. So for instance, we're running a campaign for Microsoft Azure. So I'm collecting data about all of your browsing behavior. Well, not really yours, it's more than the yes, but you know, bear with me. So I have these browsing histories of what people look at. And ultimately, when I run a campaign for Microsoft Azure and they want to know who's mostly interested in downloading a white paper or signing up for a free trial or whatever it may be, then I have to build a model that predicts that. So of all of this information, this becomes the thing I'm trying to predict, whether or not a digital device will show up on the Microsoft Azure homepage based on pretty much everything else I know that the device did. So that's my usual predictive modeling problem. And we build literally 10,000 of these models every day across all kinds of things that our clients want us to target. So this is just one of them, and whoever wants to discuss technical details, I'm kind of written them out here, but I'm happy to go into arbitrary depth on this stuff. But basically, this is one of these models. It's the top most important, kind of most predictive websites. So this model has 360,000 non-zero terms. So whoever tells me that logistic regression is an easy model or simple model, I beg to differ. It was recently, it's a streaming update, all based on 217 positives. Any case, you see what you would expect, some stuff related to technology. The hashing shows you some hashing collisions here. Doesn't really matter, just to give you an example of what the models look like that we're building. So that's the necessary kind of backstory to show you what happened in 2012. Over a period of about 2 weeks, the median lift over hundreds of these models doubled. And I hadn't done anything. And I don't believe it's the death of free will either. How can it be that human behavior all of a sudden becomes a lot more predictable? There are a few legitimate arguments why this may happen. Hey, maybe there's a new data integration. All of a sudden I get so much more valuable information, like the likes we had in the earlier example. So it could be that somehow more information came into the process. But when we started looking at what was all of a sudden so very predictive, turned out to be sites like this one, Women's Health Space. Indicated that the person was in the market for a luxury car, offers software, a credit card, pizza, and hotel rooms. I wasn't the only one. There were a whole bunch of these URLs, and I would assume that you have never heard of any of them. And what they also had in common is they had a very high overlap between the devices that went to them. So what I mean is that if you have like two host names, more than 50% overlap, meaning the same cookies show up on both of these host names. Let's play a little game. Here's a question. So I'm a website, and 55% of the devices that come to me also go to youtube.com, and 28% go to weather.com, and so on. Which website am I? Facebook? Nope, I'm not Facebook. CNN? Closer, but no. Very close. I am the New York Times. The New York Times, and you could actually see, if you look further down, you see a lot of news stuff and also something related to New York. So yes, this is the New York Times. Ha! How about this one? I have 96% overlap with Film Annex, 93 with Fork.net, and the rest of our crew that we saw earlier. Still not Facebook? Well, Hip Hop Havoc, of course. So I'll show you what this looks like as a graph. So now we kind of connect all of these websites that have more than 50% overlap. And to give you a sense what's going on down here, this is a small structure, and it's the Boston Herald. You see like it's Boston Interactive and Search. So to me it makes sense that this is human behavior, or there are technical reasons in terms of integration that explain why that happens. But what's going on there? Well, this is where our friend Women's Health Space lives. So first off, I mean, the amount of time that these things seem to have to browse the web is quite astonishing, and I also want to point out the very diverse set of interests. China on TV, clickers, wrestling news, and other stuff I can't pronounce. So there's no way in hell, there's no way that this is a human, any form of human behavior. So what you see here is basically the footprint of a new-gen bot network. that exists for the sole purpose of frauding the advertising world. Now, I'll get back to this in a second. None of this really explains why my predictability goes up, because hey, I'm predicting who goes to Azure, right? This botnet about all sites you have never heard of. Now, let's first talk about what does it mean. So they call it non-human traffic. That's the euphemism in advertising, or unintentional activity or stuff of that sort, because bot would sound too negative. So that was on the rise from 2011, from about 6% to more than 36% in 2015. So here's the business model. You create your own bogus website.com. You crawl a bunch of stuff all over the net to put some content up there. Then you make sure you have enough space for advertising, preferably video ads. And then you're trying to sell these video ads in these auctions to Claudia or anybody else who's willing to bid. So far, so good? Now, you still need people to come to your bogus website.com. Call it hip hop havoc. Now, how do you do that? Well, you could either just hire some really good programmer to write a little bot that just constantly pings your page, or you can actually just buy traffic, because there are plenty of services out there where you can buy traffic to your website. They may tell you that they're all human, but trust me, they're not. There's no way in hell that this is human. So yeah, basically it's a beautiful business model. Turns out you can do better than that. You can, before you send the spot to your bogus website.com, you send them to a legitimate website. Why does it help? Because there's a lot more money in retargeting. I'm sure you love it too. You look at a pair of shoes, and then that pair of shoes follows you around the internet for the next 3 months. That's called retargeting. Doesn't take any AI or machine learning to do that, but there's a lot of money in retargeting because brands spend a lot of money in retargeting. So that means in these auctions, if I have my bogus website and I first have the bot go to, let's say, guthyranker.com, where a bottle of shampoo costs $50 and I think 49 of them go into advertising, the bid price on those devices that had been at the Guthyranker homepage goes through the roof, because Guthyranker spends so much time and money on retargeting. So the business model is you need to have the bot first visit your legitimate websites in order to truly monetize them effectively. And this is where it becomes a problem for me, because now the bots are taking exactly those actions that I'm trying to predict. And by the way, it's not just the homepages. So if you look at the, I mean, my cynical view on advertising is that any metric that can be faked will be faked. Favorite here is the video completion pixel. So there is a technical event that indicates to the advertiser that the person actually watched all through that advertisement, the video. Now, of course, yeah, only bots are patient enough to watch through all of this stuff. So you have about 70% of all the video completes, according to our measurements, being committed by bots. What does it mean? It means that in this world that I'm trying to build models, you have exactly this scenario where there are two different populations. There are people, I mean real people out there, and then there are bots who pretend to be people. And kind of the breakdown in 2015 was about 36%. Now only a small percentage of them have that strategy, but still. If you think of what I talked about earlier, people are kind of hard to predict. It's more on the pizza side of things. Whereas a bot that was hard-coded to go to a specific website, like Guthyranker or Chase.com, it's actually quite easy to identify. So on that spectrum, you find bots almost deterministic, humans kind of hard to predict. And if you now imagine what that means for the distribution of the predictions, well, people are all stuck in the middle because the model can't tell with any certainty what's going to happen. And if you target only the most likely devices to take a certain action for the client, like sitting through the video complete, you will only reach bots at this point, because all the highest predictions focus in on that population that's most easily predicted. Now, okay, we built something that basically eliminated the labels generated by bots, and my performance went to hell, and for once I was very happy about this. What about clicks? Well, clicks is like the penultimate metric that people have worked on for I don't know how long. And in advertising, it's perceived as a measure of consumer interest. Okay, how many of you recently clicked on an ad? Right. How many of you recently had something opening up on their computer and they realized that they must have accidentally clicked on an ad? Ah, voila. So the point being here that not all clicks are made equal. And let's forget about fraud for the time being. So basically in clicks you have intentional ones, the few that may or may not exist, the accidental ones, and then let's leave fraud aside. Now, here's the irony of big data and machine learning. In a world without big data and machine learning, that doesn't matter at all. The world is a beautiful place. Why? Well, if you think of this, like there's a large percentage of accidents that happen no matter what, but if the subpopulation that's truly interested in your product clicks just at a slightly higher rate, overall the click-through rate, if you measure it, may point correctly to the fact that men are more interested in your product. But that's no longer true when you throw machine learning at the problem. What happens is that the accidental ones are almost always contextually predictive. You can predict that people make accidents, that they have eyesight problems, that they handed their tablet to their 3-year-old. All these contextual information helps identify scenarios where people click on accident. So in the end, you have exactly that problem that the accidents are very far from random. They're just accidents in our mind. The intentional clicks are still this kind of very weird human that on occasion clicks on purpose on an ad. Hard to predict, trust me. So when you optimize click-through rate with machine learning, guess what happens? You're only going to reach people who will for sure not be interested in your product. And to give you kind of evidence for this, because I kind of don't know, I see that people click on an ad, but it's hard for me to determine whether this was an accident or not. So here's the dirty secret for a very effective mobile advertising campaign. Just show the ad on the flashlight app. It's people fumbling in the dark. No matter what the creative and what the product, we always see the same list of apps having the highest click-through rates, including, not limited to, the flashlight app. So again, you really use machine learning, you bring like a gun to a knife fight, you will only find, you will have a wonderful click-through rate to report to your CMO or your CEO, don't get me wrong. But you haven't really done anything good with respect to what you intended to do. So if the kind of weakness of the metric is the issue, how about we'll look at something that is harder to fake? Like, can you predict that a person is actually physically showing up at a car dealership? Forget clicking on the car ads or going to the BMW homepage, right? Let's actually try to predict whether a person goes to a car dealership. Now, of course, now I have to come really clean about what the data is that I have. I have a lot more data about you than I let you to believe. In particular, your mobile devices also tell me where you are, unless you're super diligent about switching off and on GPS all the time. So the data that basically comes in this advertising environment, the 100 billion events that I get every day, bid requests, half of them tell me your current location. So I just need to sit there listening to the bid request in these auctions. I don't even need to bid or to show an ad, to be told 100 billion times what people do on their devices and possibly where they are. So that's, I think, some conversation we should have in the next talk on what the implications of that is. So in particular, your phone might tell me that right now it's actually a lat long that corresponds to a car dealership. Now, there is some uncertainty about this. There are problems with lat longs, and I'll talk about this in a moment. The second part is I really want to use your browsing history, and connecting your browsing history to your physical history. You need to basically do this, what's called device association. They call this crosswalk, and it's based on finding out which one of those IP address corresponds to your home Wi-Fi. And so there are statistical methods of doing that. Facebook knows everything anyway, so but I have to actually do some statistics to get there. So all this to say, I'm going to use your browsing history to predict who actually physically shows up at a car dealership. And I mentioned that there are issues with physical locations. So first off, you see this nice little grid structure here? So there are a lot of artifacts in location data if you look a little bit more deeply. This, I think, has something to do with granularity and rounding errors. But you also see what we call the Superman effect, that 30% of all smartphone users travel faster than the speed of sound, which leads me to believe that either you weren't where you started or where you ended, or either of those points. You also have people piles, kind of people stacking up 100,000 at a time in a cornfield in Kansas. So what that means is that you have really multiple populations. You have people who are the dealership and you have the right history. There are people in my data set that were somewhere else who just looked to me as if they were at the car dealership, so my label of car dealership is wrong. And there are people that may or may not have been at the car dealership, but the browsing history is from the neighbor who hacked into your Wi-Fi. So either which way, there are many reasons, coming back to these different ways a population can be put together. So here's the model that shows who actually goes to a car dealership. All right, let's take a look at this a little bit more closely. There is the in-market signal. So you see a lot of car stuff around there, and you also see like competitive brands and things of that sort. So these are the top 30 of 300,000 non-zero parameters in my logistic regression, so just looking at the top. You also see some evidence that this kind of marketing lure that people buy cars when they buy real estate. Apparently it's true, because my model seems to find evidence of that. And then something about fitness, I'll leave it to you who that person is who, when they buy a BMW, also sign up for an expensive gym. But that begs the question. I mean, basically I told you all of the things that go wrong. This looks surprisingly good as far as I'm concerned. That's a model that actually makes sense. So let's switch it around and ask the other question. How much randomness can a model absorb? How many of my labels can be randomly wrong without everything falling apart? So in this problem we had gender. I'm now going to randomly reassign the gender, which is the target variable that I'm predicting. And what is really amazing that with only 50% of the original labels, meaning the other ones get randomly reassigned. I'm not saying I flipped them, I'm just saying at random I assign them a 0 or 1. You still get more than 95% correct in the top 1% predictions. That's quite remarkable. And the reason this happens, if you look at the distribution, even with only 50% of original labels, now I have men and women different colors, you still see the spikes, meaning you see that the model is a little bit less certain what's going on, but it still has the extremes of the subpopulation that where the label was correct, where it could extract information. And this is for the 25%. So this is interesting because that really means that in this case, the model works like a low-pass filter in physics. The stuff it can't explain that is randomly wrong, it ignores, and still finds a lot of signal in whatever weak stuff that I have. And so ultimately, I'm more certain about my predictions that people actually are at the car dealership than in the original labels. The original labels had all kinds of noise, but in this case they were random noise. It was different from the deterministic problem I had earlier. So, my last example, since that's worked so well, how about we go and find the elusive frequent traveler? It's one of the most sought after grew audiences in marketing. So, where do you find a frequent traveler? Excellent, my very leading picture worked very well. Glad this is good. So let us actually predict who goes to JFK. All right? And here's my model. Let's take another close look at this. Okay, so the top runner here is a website in Spanish. Jehovah's Witnesses. Okay. I didn't expect that. this makes more sense. Association of flight attendants. Right. Apparently some NFL fans, and then, and I apologize to the audience, but that's what my model told me, we have this. So, is the model wrong? I mean, what happened here? I mean, it worked really well for the car dealership. What's going on here? Well, the simple answer is, it's a lot easier to predict people who work at JFK than people who go there to travel once in a blue moon. Ex post, that's pretty obvious. Ex ante, wasn't exactly. So, yeah, the model is doing exactly what I asked for. I just asked the very wrong question here. And the last 1 minute I have, I want to bring this out of advertising, because it's vaguely amusing if things go wrong in advertising. But let's actually take a look at a much more serious application of this. So this is a data set from Siemens Medical on breast cancer identification. So we got information from 1,700 patients. Basically, the fMRI images were pre-processed. They identified candidate regions, and then these got labeled so biopsies, and so you had a subset of them that were malignant or not. All of this data nicely pre-processed, given to us in a clean data set of feature vector with 117 features and the outcome. We built a model, and it was amazing. I mean, we could improve of state-of-the-art by at least 10% in terms of the, what they call FRC rate. In fact, we could identify about 60% of the patients that we were sure were healthy, so we could send them home. Everybody was very happy with that. Except that through some random accident, somebody started looking a little bit deeper into the data and found this. This is the distribution of the patient ID on the x-axis, and on the y-axis, some model score. It's an SVM. Anything surprising in here? Well, what the hell happened to all those people? I mean, you would assume that a patient ID is something like a uniform random number or something along this line. Well, the problem is much bigger than that. Now I actually label it based on malignancy or not. Well, basically, you got really, really lucky if you were in here, because then your chances of having cancer were much smaller than if you had a small patient ID. Basically, the patient ID is the most predictive feature in this data set. Now, we didn't use the patient ID in the earlier models. Well, we did because it was a competition and we won it, but that's a separate conversation. But there's a bigger issue here. There's something truly at stake. Of course, you shouldn't use the patient ID building a model, although, what does it tell you? What happened here? Somebody pooled data from different locations in order to get a larger training set, which is kind of what you need to build good machine learning models, a lot of data. So they went out and they collected data from 4 separate locations. Now, one of them was a treatment center. One of them is a screening center. So while I shouldn't be using the patient ID, but if the patient ID is just a proxy for the location, I definitely should use the location, because it doesn't matter whether you're in a treatment center or not. And so all the model had learned, even without the patient ID being given to it, is the calibration of the machine, because the grayscale calibration of these machines is different. So the good performance we saw was not because the model had actually learned how to predict cancer. It just had learned how to back out which location it had been in the first place. So back to the original, the easy signal was something completely different from what I had hoped the model to find. And it actually was really by accident that we found that. So what is the bigger picture here? If you think of some of the implications of what I told you, and put this in the context of a lot of the most recent conversations about using machine learning and AI in all kinds of parts of our lives, from, for instance, job recommendations at LinkedIn. There's a lot of concern that people express that the model will reflect the biases that the data has, right? And if your data set is biased because you never had a successful female CEO, then you will never get a model to recommend a woman for the job. What I'm saying is much worse. I'm saying, well, even if you had a biased data set to start with, if the first order effect was taken care of, the model is quite happy and able to introduce biases all by itself based on what is easier to explain versus harder. It will always recommend what is easiest to predict first. And you saw that in all of the examples that I gave you. And that is happening when you think about the jobs that we recommend to people. There's a lot of work in the US right now about predictive policing, where police should go. And there was a very interesting case, and I know I'm going overboard with my time here, of Latanya Sweeney, who is a tenured professor at Harvard. And during her tenure case, she was Googling her name, and she was really getting upset because she constantly saw ads of mugshots.com or suggesting that she had been arrested. Now, knowing that she wasn't arrested, this was not even a case of retargeting. So what is happening here? And she spent a whole kind of research deep dive, and she found that when you typed a name that had clearly kind of black cultural association, you were much more likely to be shown these kind of ads than if you looked for John Smith. And the question becomes, is this some malicious intent that the person who owns mugshots.com kind of put as keyword search words into Google only black names? Or is this an outcome of some optimization algorithm that's trying to predict the probability of click based on what you're searching for? And it could very well be that that's what happened here. I think there was never any statement from Google what the underlying mechanism of this is. But it's an interesting example where I think this just could have purely come out of the algorithm optimizing towards what's the easiest to predict. And with that, thank you very much.